I'm going to, Ash and I this evening are going to give you updates on our, these are our post-research talks to let you know what we did with our research period and what we continue to do. Mine will end up being, my research period was, the plan was changed at the last minute and in a positive way. And so I'm going to talk a little bit about sort of things that I did, what I plan to do, and then what I ended up doing. So, you know, in aviation, we talk about planned course, and then a very nice way to say that you did something completely different is to call it navigated course, right? So you say, what was your planned course versus what was your navigated course? So where did you get lost, basically? And then I'm going to talk about sort of what I foresee going forward and what is still going on, because I think like probably a lot of residents, what's happened is the 6 months of research period basically got everything started, and now everything's really cranking along. So like we're getting busier and busier. So first, just with what I set out to do, Dr. Blevins is my mentor, and I'm very interested in all things related to patient safety, and one of them is patient-specific rehearsal. My interest in this obviously comes from my background in aviation and simulation. What we set out to do was to work on a study design for simulator development, built around patient-specific surgical rehearsal. And the paradigm we're trying to use is basically we have a collection of intraoperative videos in HD, and we've also got just scans, CT scans for those same patients, and in some cases MRIs. What we're trying to do is kind of do a patient-specific simulation in reverse. We take the intraoperative videos, and then retrospectively we go fetch their image data, load it onto the simulator that Dr. Blevins' lab, Sunny in particular, has been building. And then we try to reproduce a model of that patient's anatomy. And through a process called segmentation, we highlight anatomic structures that we find interesting and we'll want to stay away from in real life. And then what we do is we try to see if we can reproduce on the simulator what we saw and what we have a record of on the videos. And we're able to do that. What we're trying to do specifically while I was working in the lab was we're trying to figure out how to do this with commodity level technology to make it accessible to physicians so that we can get clinical yield from this at some point. And we're there, and depending on the user, myself being sort of a non-technical user, and Dr. Blevins and being a more technical user on the software side, we can do some pretty remarkable things. Part of the emphasis on what I wanted to do was actually participate in the actual design of the simulator with Sunny, bringing in sort of a clinical perspective and then my background with training in simulation and sort of philosophy and science of simulation, and seeing if I could help them change come up with good workflows within the software. Here is just sort of representation of sort of a proposed workflow. We normally get patient scans, and normally we look at CT scans in the traditional planar views. We'd like to replace that with a virtual representation of that patient that we can operate on in a simulated environment and then proceed the operating. Again, so I was working a lot on user interface and workflow integration as part of this project. And then another goal that I had was downstream we want to be able to do more prospective work. Once the simulator is where we want it to be, we want to be able to take patient data and preoperatively simulate cases and see if we can achieve any kind of measurable change on outcomes, or just see if we feel like there's any additional benefit from that. One way we're thinking about doing that in the future is to do a cadaver study where we scan cadavers. And you'll see that we've actually done the initial we're working on sort of a trial run of this. We've got some cadaver heads scanned, and through the very generous contributions of Dr. Peter Santamaria, he's actually compiled a big database of 3D high-definition videos from the lab of almost every urologic approach. And we've got the scans from those same cadavers, and we're going to be able to put together a really nice resource for the residents. So there were simulation projects, but then, what worked out well for me and what I think I accomplished with that piece was I had actually a high technical learning curve, specifically with the software called, we use a software called Mira to do the image processing, to take raw DICOM data and segment out the anatomic structures that we're interested in. That doesn't happen automatically. There's no software between the baseline data and the quality of the capability of the current software. We can't do that automatically. So it actually took me quite a bit of time, longer than I anticipated, to learn that system and to be able to do it well. And still, compared to like Peter Lee or Dr. Blevins, I'm immature at best. But I feel like I got myself to a point where I could reliably take raw data and produce what I wanted to simulate. Here's just an example of a video of an intraoperative video from a cochlear implant patient, and then a really rough, quick representation of the same anatomy. And then I feel like I had a lot of contribution in terms of the sim design. Those pictures are something we use some mock-ups to communicate back and forth with the software team about how workflow should look inside the simulator. So that, and the goal here is that non-technical technical users, surgeons in the community, could use this kind of technology. So we're trying to get it to a point where you can just take raw data, load it in, and very easily translate that into a high-resolution, workable, three-dimensional surgical design. We got a long way, and Sunny is tirelessly working on actually coding the simulator. I think it's on its third version now. And then we did, like I mentioned, achieve at least feasibility from the cadaveric side. We've got scans that we're going to segment out and produce. These are cone beam CT scans we've been using and from our clinic. And again, we've got really great, unbelievable high definition 3D videos of the same specimens for all the information. So obviously, one of the things that occurs when you're doing this is sort of setbacks or things you didn't anticipate. Again, like I mentioned, a much longer technical learning curve than I anticipated. The theme here is going to be everything took longer than I expected. Data management hurdles greater than anticipated. That is a really nice way of saying one of the goals early on was to figure out a good system of getting raw DICOM data from our PACS systems into our simulators in a way that was HIPAA compliant and complied with the IRB requirements. That is much easier said than done, apparently. And it's a lot of negotiation between the GB people and the PACS, and partially because I'm sort of unskilled technically, but that was more difficult than we anticipated. Though Dr. Blevins and I think Pete Lee have figured out a good workflow at this point. And then the software side iteration cycle, so just in terms of planning, like how long it takes to build new features into the software. Unfortunately, Sunny, who is amazing, is only one man and can only do so much coding and has a lot of projects going on. It's really, to do it right, it takes a while to get the features built in that you want to be done correctly. That's actually not a bad thing. I think it's just the expected time frame within a 6-month research period. And then the second thing that I did, which really sort of changed a lot of my plan. At the last minute, I was able to participate in a biodesign innovation program here at Stanford, which turns out to be a really incredible experience. And I think it really changed my outlook on not only sort of my career, but also the way I think about patients and clinical problems. Just in terms of the way this program is structured, it's available. They do it every year. It's the core component of the bigger biodesign program. It's a 6-month team-based, intensive, and immersive program where you get divided up into multidisciplinary teams, usually including engineers, either medical or basic science people, and usually one person from the business school. The idea is they're trying to teach the process of med tech innovation, not pharmacy, not pharma. And specifically, they're a little bit device focused, but broadly, they try to teach a very specific framework for approaching innovation. This is kind of they have this textbook that they've published. It's Paul Yock and Zenios, Dr. Zenios, who actually lectured here recently at Grand Rounds, and Josh Nickower, who's an internist, but I think he's never practiced, but yet he started at Clarence, and he has a device incubator called Explore Med locally. So they've come up with this process, and they wrote this in their textbook, and they structure everything in the course around this. And they've done this over many cycles with many people and lots of fellows and many companies, and really they've translated a lot of technology into patient care using this methodology. So the course literally follows that. You're broken up into a team. This is my team. Paul is a cardiology fellow here doing molecular imaging. Sheila is a master's level mechanical engineer, and Ed Wilkinson is a former consultant with experience in diagnostics industry, who's a business student here. We were given a clinical problem. You're not allowed to choose, and we ended up with kidney failure. So I spent a lot of my time on my research rotation researching kidney failure and kidney transplants. Not something I expected, but it was the idea and the concepts that were important. We focused in on actually the transplant crisis and the failure rate for graft failure. This is a really challenging clinical area, and it's also a challenging area to innovate in because it's not a big group of patients. They're very, I don't want to sound callous, but they're very costly patients to the system and in terms of suffering. And yet it's very difficult for companies and researchers to get traction with innovations in this space because there's not a lot of money. So we were trying to work our way to detect kidney rejection earlier, basically, in transplanted patients, so that we can extend organ life and prevent failures, essentially. We came up with this bloodless, at-home, connected creatinine monitoring device, which in theory would work, but we're never going to build it. And there are reasons for that, but it was designed to bring the patients back into the system. My role on the team was right away really, because I was in a position to do so, I was able to give them a lot of time, and they reciprocated by asking a lot of me, which was great from my perspective. But I did a lot of, spent a lot of hours working on this. It's 8 hours a week in class. Did a minimum of 10 hours a week outside of class and in meetings, and the background work that I was doing and producing for this team was actually, it kind of boggles my mind a little bit when I look back at what I ended up producing for them. Obviously, as the doctor on the team, I was responsible for one thing, teaching these guys the background, the medical background, which can be very challenging. And especially as you start moving into trying to come up with solutions for these problems, it's really important to be simultaneously constrained by what is considered possible or feasible by somebody with medical background, but also not limiting yourself. As a doctor, I found myself constantly saying, no, there's no way we can do it. People would throw out ideas, I'd say, that's just not going to work, etc. And I had to train myself, and they're very forward, training you to sort of drop that out of your brain for a little while, at least be open. So I spent a lot of time segmenting out clinical problems, doing lots of deep research in the clinical need area, and trying to figure out which patients fit where, what were their problems, were there actionable sort of therapeutic targets we could go after. And as the only ND, well, me and Paul Cam, the other ND on the team, this was sort of our charge, was to educate and produce a lot of this kind of data for them. When it came time to do solution development, again, like I said, it was really important. Our input was really critical to the team in terms of making sure we sort of stayed on course, but that we didn't sort of stifle people's innovative drive. I did a lot of research and produced kind of like white papers galore. Just, I mean, this is a paper I had to write them about just how the kidneys work. I wanted to shoot myself. Because, I mean, you know, I was literally talking about nephrons and stuff. Thankfully, the other guy was a medicine doctor, but again, he was really busy outside, and I was stuck doing this, so it was quite an experience. But it was great because I had to learn how to think about those problems and make them very accessible. And we're talking about the kidney, which I think most of you, even nephrologists, don't understand. And then I learned a lot from, especially Ed, my partner, and what they insist that, you know, and this was really interesting to me, that you learn how this works from a financial side, because it's really important when you're thinking about translating things into and getting an idea to a patient. There's a million good ideas that should be built, but they're not all going to be built because there can't be money behind them. So you really have to understand how that works, and part of that was learning how to do financial modeling, and a lot of the business stuff I'd never really been exposed to. My takeaways from this experience were really, they're very need-focused, everything. They're religious, fanatical about clinical need. They believe it's the fundamental aspect of innovation because, as they say, the ground is littered with companies and ideas and devices which are great pieces of technology but fail to address a real clinical need in a meaningful way. So that process and enforcing that sort of that discipline on you, it really has changed the way I think about clinical problems and these conundrums we come at. I find myself much more sort of algorithmic in my thinking about things. Much more deep, like I said, understanding of why some things get built and why some things don't. Probably like a lot of you, I think a lot about this. I will say, why don't we have this kind of? Why is this not available to me? And usually, there's a really good answer for that. And then a lot of the details, like intellectual property, regulatory, which was very important. And I was actually on the team. Part of my responsibility was a lot of the regulatory strategy. And then, of course, reimbursement, which was a little bit more accessible to myself and Dr. Kim than the others. And that was another thing that was difficult to educate people. And then really working with that multidisciplinary team, as I mentioned, was challenging, but really interesting. And then a third thing I did during this time, a lot of this was spawned by my involvement in biodesign and some of the people I'm up there, and then some of my background interests. I'm really interested in healthcare delivery systems and patient safety. And as some of you know, we've been working on a project for care coordination for image sharing that's HIPAA compliant, and we're working on that actively. I've done a presentation on this, and this is ongoing, this cloud-based point-of-care image capture and sharing mobile application we're working on. And it's actually done. We're just waiting on Stanford to tell us it's okay to use, which is probably not forthcoming anytime soon. But it's been built out. Actually, initially we built it out for the outpatient side because it was much easier, and we built it around a dermatology need. But the way it's going to work is going to be exactly the same. It's going to be essentially cloud-based image capture, which is automatically HIPAA compliant, but it's also going to have the ability to communicate and collaborate really easily. My hope is that we can use this here in our residency program to really improve the care we give to our patients, because we spend a lot of time tracking our attendings down and our colleagues down, and we miss a lot of teachable moments by repeating scopes and put patients through multiple scopes in a lot of cases. We're currently also developing this, like I said, around the surgical care delivery models, and specifically we're interested in post-op wound care, flat monitoring, and even transitioning to outpatient. So what I sort of foresee going forward for the simulation work, the cochlear implant project, we're going to wrap up and write a paper on at some point in the near future. And then this new cadaveric, so Dr. Santa Maria has been just incredible and really given a lot of his time to this. And we'd really love to build a resource for the residents here, a training resource that we can essentially reproduce common, all the otologic approaches, and we'll have great 3D videos and we'll be able to simulate those in 3 dimensions in the same anatomy, which is really exciting, and we're starting work on that. And then for the delivery systems project, we're moving this it's actually taking a step up a notch, and we're getting they've written some APIs, which are programming interfaces on that cloud software to connect with consumer devices that are starting to collect health data. And this is a screenshot of, it's a little cheesy, granted, I didn't design it. But the idea is that we're going to hopefully be able to sort of integrate patient data that's out there being gathered and unused. That's kind of the basic problem we're trying to solve, is can we leverage and use unstructured data to achieve better care for our patients? And I have a strong interest in patient safety, and as I see it, a lot of this ultimately relates back to that. So it's just special thanks to Dr. Blevins and Pete Lee, and Sunny Chan, who's the PhD candidate who is runs over in the lab. Jonas Forsman also works in the lab. Dr. Messner, and especially for letting me. The Biodesign program took me over. It's 4 to 6 p.m. on Tuesday and Thursday, which means I had to miss Res Ed, and often it would go late, and so I would often miss grand rounds for almost 6 months. And that required a lot of understanding from them, and I really appreciate it. I think it's an experience that you can't get anywhere else except for Stanford. This is a program, this kind of environment doesn't exist anywhere else. So you can't get this kind of training, I think, in place. And Dr. Longmire is my sort of collaborator with the image bases shared. So that's it. I just would love to take sort of suggestions or comments or questions about the work we've been doing.
What comes to mind first is, why did you do so few things?
That's a problem. The problem is that honestly, that's the biggest problem I had was choosing, and I'm still having that problem. Because the way this works is the more people I met, the more I got involved. The way Biodesign is just kind of like a cancer. You start working with these people, and they're like everywhere. You can't, I mean, like everybody's calling everybody, and hey, I've got this thing, maybe we can do this. So it's great, and it's a testament to the sort of the power of that program and Stanford. But it's hard to choose, and you know, my time, all of our time is limited. So that's going to be my biggest challenge.
Yeah. So I'm incredibly impressed in all the things you're doing. I just wonder like it. But one thing is that we use SMS texting all the time for patients, and it's a big leak in privacy because there's no protection for it.
Yes.
So you're very forward-looking and looking for ways to exchange. There are a number of commercial entities out there. Stanford has just decided to go with Metagram.
Yeah,
so
it's a local company.
That's coming out pretty soon. I was just looking to see whether Metagram will handle images. I don't see anything that they will.
So they do have, and they've got a companion app called, so Metagram is a local company that was incubated out of StartX, which is a nonprofit Stanford student incubator. I don't know the people who started it, but they built it around the text messaging functionality, and they are adding image share.
Yeah, because that's under, so my guess is, when it comes to privacy, you'll have to use their blessed service, and they'll probably not open it up to other things. And although right now, you see all of this huge effort around encryption and backup and all this password complexity and all that, pretty soon the SMS thing is going to crack down, and they're going to start monitoring, and it's going to be an issue. And for all of you who haven't yet taken the new HIPAA course, it's due, it's overdue. I hate to be the bearer of that bad news, but pretty soon they're going to twist my arm to twist your arm to get it done if you haven't done it. The residents had to do that too, right? The new HIPAA thing? Yeah.
Well, ours is covered, actually, I think, we've all done it.
Well, we all have done it multiple times. This is a new one.
they get online stuff right online before every new year, like in June. So I think they got it.
I hope so.
I'm sure they did.
I hope so.
So to send a page, we have to type in a 14-digit secret code now?
Yes, that and sell your firstborn child, and if you have the new iPhone, stick your thumb on it. I don't know.
Actually, interesting.
It's the same one the CIA is using to get into SMS.
Oh, God.
Speaking of the new iPhone that was released, it's interesting that Apple, when we come to connected devices is something we're really interested in. And Apple, part of their big release is the new phone has some second chip so it can run its sensors while the phone is asleep, and they specifically made mention of health and fitness apps. And additionally, Apple is also reportedly going to be releasing some iWatch, some wearable things, and they've hired a lot of health sensor people, and they're very secretive, but a lot of people think they're going to take this sort of. But nobody knows how the FDA is going to react to any of this. These are not regulated devices, so how we can use them in our practice is going to be something that has to be worked out. Oh, thanks.
All right, everyone. So my post-research presentation, I just wanted to talk to you guys about. Oh, this is a thing actually. All right. My research mostly in the Dr. Samou's lab. Just a little bit of a presentation. Mostly, this part mostly pertains to the juniors if there are any here still who haven't done the research period. Is I just wanted to give you a little bit of advice about the pre-research and research period. I think one of the most important things that you should do is choose your lab early and choose in a field that is related to what you're interested in. Because if you're interested in the work, you're obviously going to work harder. And picking your mentor early will help you figure out what project you're going to choose in the lab and what project you're going to work on and so on. I was, I think, I'm not sure if I was the first person that did this, but initially I went outside the department and I chose a mentor outside the department because I was interested in a particular project. And it was really an interesting process because I had thought I had confirmed with that person that I was going to join the lab and so on, and it turned out that 6 months had passed and they hadn't heard anything from me, so they had figured out that I was no longer interested, so they took somebody from their own department into the last spot in the lab. So Dr. Samou was very gracious to take me into his lab and come up with a project for me to do, which was amazing. I say that you should be realistic, set your expectations high, but be realistic and choose a project that is already up and running because you're not going to cure cancer in 6 months. Proposals are due about a week before. Again, reiterate a lot of things I said. Make sure you have kind of gone over your PI before. And really, it says 6 months, but it's really 4.5 months because 3 months of it is really half time. You have clinical duties. You're part of the regular call pool, and you are expected to kind of get the VA. So, although that is not terrible.
We know.
So work efficiently during your research time. One of the things that came up a couple of times during my research block when I was on half-time or when I was actually at the VA full-time with other residents on the research block, is that make sure if you really plan to do experiment, let your chief know. Because if you don't let your chief know and there's a clinical need and they ask you to come in, you don't want to be in that position where you have to choose between your experiment and letting down your chief. So and the team. So I think just if you have an important experiment, just let your team know. And the other thing I would say when you're going into your research block is diversify. What I did was I picked a basic research project, but I also worked on clinical projects, and I won't be talking about that today. Mostly I'll be talking about basic science. Post-research, really try to finish everything before you leave. Nothing is really going to get done very quickly once you have that. One of my philosophies about getting papers done is that you always should think about the figures from the moment you join the lab, and think about how many figures you have and how many figures you need in order to publish that paper. And I think that goes a long way to really get you focused and doing the work that you need to do. And then at the end, go to as many meetings as possible. Boris is really right at the end of the year, right next to our research day, and I recommend it highly to all the residents. You should really go, and you meet a lot of awesome faculty locally, and you get to meet a lot of residents. So I think, and you're required to go once during residency, so this is the perfect opportunity. So as you guys know, my project in the lab was with toll-like receptors. Toll is basically the innate immune response receptor for recognition of bacterial pathogens, viral pathogens. This has been really a hot area in recent years, especially innate immunity. And more recently, it has become a topic of interest in cancer. And that's what Dr. Samou's lab has been interested in. There are 9 or 10 toll-like receptors in various mammals. Some actually have up to 12 or 13. And they upregulate a bunch of chemokines and cytokines, things such as TNF and IL-12, and they all occur through NF-κB and kinase pathways. And this is just kind of a little background slide. Dr. Sunwoo's lab, Lovisa, who was the former postdoc in Dr. Sunwoo's lab, had figured out that actually a lot of the SECC6 cell lines in the lab express toll-like receptor 2, which is one of the toll-like receptors that is that I showed you earlier. And this one is important for recognition of yeast and bacterial cell wall. So this was kind of interesting to us trying to figure out if this was playing a role in tumorigenesis. And Lovisa also has some nice data showing that when you look at organoids in the culture, when you have a toll-like receptor 2 stimulation, you get increased organoid formation. So kind of supporting some sort of a hypothesis that yes, the toll-like receptors may actually promote survival. But one thing that we didn't know is that toll-like receptors are really well described in immune cells. They're not really described at all in epithelial cells, let alone cancer cells. So we had to see if this was really occurring through the same pathway, and we were getting really stimulation of the really canonical pathway of toll-like receptors. And that was really through showing NF-κB activation. So the first thing that Dr. Sunwoo and I had discussed going into the lab was using a surface reporter system to come down to see whether zymosin stimulation, zymosin is that toll-like receptor 2 ligand, will activate NF-κB. And we used the luciferase reporter system. I'm not sure if you guys are familiar with this, but basically the luciferase gene, the protein, catalyzes a reaction that results in visible light. You take a plasmid that has this, you get your promoter of interest, and you put it right here, you subclone it in. And then you put it inside the cells, you look at the conditions that you have, and then you see if you can get luciferase activity. And then this is kind of a good way to look at transcription factor activity. I was lucky enough that my old lab had this already working. I had actually used this particular reporter before. I called them, they sent it to us, didn't work. And I was very surprised because I had used it probably 50 times in my old lab. So I was like, they're either trying to sabotage my work or so I ran the plasmid out, the plasmid looked perfect, the maxi drug was perfect, and we started to suspect that maybe our transfection efficiency was not good, or maybe the plasmid that was sent was not the right one. So Dr. Sunwoo had some colleagues at NIH. They sent us another reporter, and same thing. So we went to the troubleshooting phase and tried to figure out what was going on. After multiple rounds of experimentation, I found that the problem was not really with the assay itself. The luciferase assay was working based on cells that already had luciferase overexpression. But the fact that the cells were just not getting transfected well enough. And we tried multiple different transfection agents, including Eugene and lipopectamine, a lot of different conditions, and we just I just couldn't get it to work. And it was kind of a humbling experience because this is one of the most simple experiments in molecular biology. So I was like, all right, so let's make things more complicated. Since we couldn't get the simple stuff to work, we'll make the more complicated stuff work. So we went to qPCR. qPCR is basically looking at mRNA expression. And if you guys recall, we had talked about inflammatory cytokines being expressed because of toll-like receptors, and we wanted to see if these cancer cells would respond the same way. Now, I really had no reason to believe that they would because they're obviously not immune cells. But the first experiment was very encouraging. We were just jumping up and down. And this is kind of true for a lot of different cytokines we tested. This is qPCR looking at cells that were stimulated with, this is just media, zymosin for 24 hours and zymosin for 48 hours. Now, I couldn't explain what was going on here, but when I saw this, I was like, whoa, this is good. Although, you're looking at really a twofold induction. But even that in epithelial cells was really exciting. But there was something a little fishy. I couldn't really explain why at 24 hours you would get a downregulation of TNF. And I was kind of trying to remember why at 48 hours you would get an upregulation. And I remembered when I collected the cells, the cells looked a little bit unhappy. They had been in the culture for about 48 hours, and they're just, not happy. So I figured maybe that could be a contributor. So I went back and multiple experiments with qPCR. Unfortunately, at great cost to Dr. Sung Woo. There's just some of that read, and that I promise that other people in the lab can use it. But what I found was that when you look at various cytokines at different time points, if you change the media and keep the cells healthy, I couldn't get really any discernible differences. And this is probably because we're not really looking at the right genes. And finding the right genes using qPCR is really tough because you really are going to spend a lot of money running qPCR day and night. So I scratched my head a little bit, and after Dr. Sung Woo, we decided to actually go back to look at the protein, NF-kappa B and ERK, or the two proteins we talked about. They're both downstream of TLR, and they both get phosphorylated and they translocate into the nucleus. So we decided to just stimulate cells as we had done before, and look for phosphorylation. We knew it had to look really early, and after a lot of optimization and so on, we were lucky enough to be able to show that zymosin actually does induce D65 phosphorylation. Now, there's a lot of problems we encountered along the way, as Dr. Sung Woo has actually published the data before that the head and neck cancer cell lines have really high basal activity of D65. So getting them to the right condition where they didn't have that high basal activity was tough. And honestly, I still to this day, I still don't know what are the perfect conditions, because you still get, if you do duplicate, sometimes you get one well that's just really high and one well that's not. But we were able to show that phosphorylation of 65 occurred with zymosin, and that it went away when you blocked it with Colic receptor 2 antibody. That this was a specific effect. TNF is a really much more potent inducer of NF-kappa B activation, and we were also able to show that D65 and ERK both got activated with zymosin at various time courses. This was really all this data kind of came together towards the end of my time at the lab. It really took 6 months to kind of go through trial and error and figure out the experiments and so on. And I'm not really going to go through and show the final product of the data, but we have some future plans for our project. We're trying to figure out how Colic receptor 2 potentially play a role in human cancers. We're doing staining in samples from human tissue, and we're trying to correlate that with disease. And we're actually trying to set up a collaboration with Kaiser, and Kaiser has a lot of the annotations with outcomes and so on. So we're trying to get a tissue from them and do a high throughput screening to see how the tumors express receptor 2. The manuscript is, the first draft is really written, and we're just kind of putting the finishing touches and kind of working through some logistical issues to kind of get everything set up. And I think hopefully by the end of this academic year, we should at least have it in review, but you never know with these things. We're working on it. So at this point, I'll just open to questions. I just wanted to really thank Dr. Sung Woo and Lovisa and all the people in the lab. They were very awesome, and they took me in, and were very kind, and I think we did a lot of